Yes, welcome. Hi, my name is Shaban Mchung, and today we are going to see the solving session concerns the topic of integration, a part of calculus, and we're going to see question number 9, Advanced Mathematics, Paper 1, 2023. So normally in the format of these Advanced Certificate of Secondary Education examinations, it is question number 9, integration. And now the question says, part A, find the following indefinite integrals here in Roman 1 and in Roman 2. Integrate x over the square root of x plus 1 with respect to x. And the same apply now to Roman 2. Integrate theta square e raised to 2 theta with respect to theta. So these are indefinite integrals, and once we are integrating them, we need to leave the final answer with the constant. And we are not going to get exactly the constant number. So we just remain with the expression as an answer. Now solution. Solution in case A, Roman 1. Here we have infinite integral, that is x plus 1 with respect to x. Now a question like this can be solved through the direct substitution. And here we find the situation where now we can so it can simplify the other parts. And normally in integration, we apply differentiation. So that's why we say integration, differentiation, they're just opposite to each other. So for example here, if I use direct integration, substitution, maybe I can apply by directing substitution. That's maybe we setting u equals to the square root of x plus 1. So we have let this denominator expression equals to u. That's the direct substitution. So here, the same as saying u square is less more to x plus 1. Now from there we can integrate, we can differentiate with respect to x. So here it will be 2u du then dx, because here we differentiate explicitly, but here we differentiate normally. So here it becomes 1, and this one, it is a constant, so it becomes 0 once differentiated. Now from there, we can make subject x dx, so as we can come and substitute this x dx in terms of the other variables. So maybe here it will be like, maybe it's 2u du equals to, once multiplied by dx both sides, so we'll have dx. So now we know dx now is now replaced by 2u du. Now from there, again, now we can say then. So now it's going to be integral of x, but our x here, if we make subject x here, x becomes u square minus 1. If we make x the subject there. So here x, we substitute that u square minus 1, and over the square root of x plus 1, we know it is u. And here now dx becomes, it is 2u now du. Now from there, all the variable that does not concern, all the variable that do not concern with the respect, that's u, they have to be taken out of the integration sign. So here we can take out that 2, and now we have 2, then now we have u square minus 1 times u now, then over that u, then here we have du. Now from there we can simplify. This u and this u now cancel out, so we remain with 2 integral of u square minus 1, then now du. From there now we can take integration sign with respect to u inside. So we can have, now it is 2 then integral of u squared du minus integral of u du. So from there we can integrate now, very simple. You integrate by the power rule of integration. So that one now becomes, it is 2 outside, then this becomes 3, because integration means summation. We just increase the power by 1. So it becomes 2 plus 1, that's 3, over that 3 now. Then we minus u. Then now we plus the constant c. So from there, we can take this inside, so it can be 2u cubic now over 3 minus 2u now plus c. But remember where we said u was the square root of x plus 1. So from there, we are going to have 2 that x plus 1 then cubic now over 3 minus 2 then the square root of x plus 1 now plus the constant c. So from there now we have integrated the function now with respect to x, and then now that's the definite integral solution. X plus 1 cubic over 3 minus 2 the square root of x plus 1 then plus c. So that will be now the definite integral for this integration of the expression there. Yeah, so that was Roman 1. Now let's see Roman 2. Now in Roman 2, here we are told to integrate theta square, Euler raised to 2 theta, then now theta. Yeah. So this here is the combination of the algebraic function, and the exponential function. So when they are combined now, we can apply integration by parts. So that's a technique that we are going to employ here. So it will be easy through integration by parts. And our solution, so we can say through integration by parts. Now, the letter of respect is the theta, so we can use this formula that if we integrate u dv equals to uv minus integral of v du. So that's the formula that we are going to apply here, integration by parts. So we need to differentiate the parts of algebraic function, but we can integrate the parts of the exponential function. So from here now, we equate with this one. It means now u is less more to theta squared. So from there, we differentiate du with respect to theta. So here now becomes du d theta equals to 2 theta. Again, we want to know what is v, so we can take this dv now equals to e raised to 2 theta now d theta. Yeah, so we equate dv is equal to all these. Then from there, now we apply integration. We want to know what is the value of v. So on applying integration now, it will be integral of dv equals to the integral of e to theta now theta. So here we'll have v now equals to, when we're integrating exponential function, the simplest trick is like taking for these Eulers functions, we take 1 over the derivative of that power. It means the derivative of power here for 2 theta is 2, so we take 1 over 2. Then now we times the original exponential function, e raised to 2 theta. So that would be the value of b with the simple trick instead of substitution. But you can apply substitution. You can just let maybe p equals to 2 theta, then you can perform this substitution calculation. But at the end of the day, you'll end up getting v equals to a half e raised to 2 theta. Now from there, we go back to the integration by parts. Now we can say this, which is that. So we can say then, integral of theta square, e of 2 theta d theta, is less more to say uv, so u is theta square, now times our v here, it is a half, which becomes this way now, 2 theta. Now we minus integral of v, which is 1 over 2 e of 2 theta. Now we times du. Now du here, du if we make subject here, du now becomes, it is 2 theta, now d theta. So it becomes 2 theta, then d theta. That's become the value of the du. So from there, we are going to have theta square over 2e of 2 theta. Then here this comes out, so we minus integral of e, here it is theta now, at the back, then e of 2 theta, and then now d theta. So from there, we still have this algebraic function in combination with the exponential function. So again, we go back for integration by part. Then we come to combine with this one. So from there, we can say also, for this one, theta, e of 2 theta, now d theta. So from integration by part, u dv equals to uv minus integral of v du. So we can say again u equals to theta, then now du d theta equals to 1. Du d theta becomes 1, or we can just say now du, if you multiply both sides, but d theta, you get now du equals to d theta. Also, dv now equals to e raised to 2 theta, now d theta. So if you apply integral both sides, it becomes here d theta, and then now it becomes 1 over 2, the same trick that we take the reciprocal of the derivative of the power, that is 1 over 2 times the original exponential function. So that becomes the value of v. So from there, integral of theta, e of 2 theta, d theta now becomes u, which is theta now, this one here, times v, which is a half, and e of 2 theta. Now we minus integral of v, but our v it is 1 over 2 e of 2 theta. Then du, it is the same as d theta. So from there, this one now becomes e of 2 theta. Now we can minus this 1 over 2 outside. Then now once integrating e raised to that much, we get now this one. Then now we can say plus c. So from there, we'll have theta over 2 e of 2 theta. So here we subtract 1 over 4 e of 2 theta now plus c. Now this one, it's a value of theta, then e raised to 2 theta d theta, which is this one here. So now we come to combine, so you can have now, then integration of theta square, e of 2 theta d theta, is less more to say theta square over 2 e of 2 theta. Now we minus all these, minus this one, minus this one. So we minus theta over 2 e of 2 theta. Then that's negative times this one becomes positive 1 over 4 e of 2 theta now plus c. Now we look for the like terms where we can operate. For example, here, yeah, it's the same in terms of e raised to 2 theta, but here there is theta square 1 over 4 itself. So we can just leave like that, or we can factor out. If we factor out e raised to 2 theta, now this becomes minus theta over 2 plus 1 over 4. Now, then e raised to 2 theta now plus c. So this becomes the value of the definite integral. This one. So that's become that. But also, we have the simple technique by tabulation method. That's where now we can calculate and see how we can reach here. So we can perform that tabulation for proving. If it's happened, you have algebraic and in combination with exponential trigonometry, we can use that method of tabulation. It only works for algebraic and the other functions, where we integrate algebraic until we reach 0. If the functions are not algebraic, the other form maybe trigonometry and exponential, the tabulation method cannot work. So by tabulation also, alternatively, so by tabulation method, here is a table where we differentiate algebraic function. Here is a differentiation part, and here is where all functions which are not algebraic. So you can have two parts. Here we put algebraic, and here we put that exponential. Now you start integrate. You differentiate several times and integrate several times. But we differentiate until we get 0, then we stop. So here it becomes 2 theta, then it becomes, when we integrate this one, we will have 1 over 2 e raised to 2 theta. If you differentiate again, here you get 2, and here now it becomes 1 over 4 e of 2 theta. If you continue differentiating 0, then here now becomes 1 over 8 e of 2 theta. Then you stop when the derivative, the multiple derivative for algebraic function becomes 0, we stop. Then now you perform a zigzag manipulation, and here you start with positive, negative, then positive. So you start with positive followed by the negative, positive, and negative rule. And not negative to positive, we start with the positive. That's where the method can work. So you leave these two, this one and this one. So now you find the product. Now you say integral of this one equals to this times that times positivity. Then you get theta square over 2 e of 2 theta. Then this times that times this negative, we minus, then here 2 and that one you get a half. Then theta e of 2 theta. And again this time that, we get positive. 2 and 8 you get 4, 1 over 4 e of 2 theta. That's where now you add the constant c, because here we don't have the limit. So you can see they just look the same. They just look the same. So this is the best approach to prove your answer after integrating by part technique, where you need to have algebra where you differentiate until you reach 0, and here it can be the other function, exponential, trigonometry, whatever, but algebraic it has to stay to the part of differentiation, so that the method can work. Okay, now we are switching to case B. So we are proceeding with the part B. We are required to find the volume of the solid generated by rotating about the x-axis, the area enclosed by the solid equation y square minus x square equals to 4 and y equals to 0 between the intervals along the x-axis, that is x equals to 0 and x equals to 3. Now, solution, the volume of the solid V is given by the formula integral of pi y square dx. Then now the limit x naught to xn, the higher limit. Now from here we have the equation that is then from that y square minus x square equals to 4 and y equals to 0. This is along the x-axis. So from here we can make subject that y square, as you can see from the formula. So if we make y square the subject, we get 4 minus plus x square. So from there now we can go direct to the formula that v is less mod to integral x naught here from the equation that have been given the intervals from 0 to 3. So here the lower limit, the higher limit. Now here it is pi now bracket, then we put 4 plus x square now dx. So from there we can take out pi, it's constant. So it will be pi integral, here is 0, 3, then now we have 4 plus x square dx. From there now we can integrate individually every term. So here we'll have pi. So here I'm going to have 4x. Now we plus x cubic over 3. Then now from 0 to 3. So here it is going to be, yeah, it's pi. Then now we plug the intervals. That's when you put 3 here where x, we get here it is 12. Now we plus, it will be 27, 3 cubic, 27, we divide by 3, now we get 9. Then now we subtract pi again, now we put 0. So 0 here becomes 0 and 0. So at the end of the day, now we get this plus that, we get 21 pi. Then that's now will be the volume. So now generated about the x-axis now will be given as, so we say the volume equals to 21 pi, but we know volume it is unit cubic unit. Yes, so this now will be the volume generated. Thank you.